Hello, I'm Dr. Seth Kessler from the Metis Design Corporation, and today I'll be talking about our Phase 2 SBIR guided wave-based bondline integrity monitoring. The Metis Design Corporation is a small technical consulting firm headquartered in Boston, Massachusetts. We offer novel multidisciplinary defense and aerospace solutions, including structural health monitoring and multifunctional materials that incorporate carbon nanotube assemblies. Over 60% of our staff hold PhDs, and we have hands-on experience from priming over 60 SBIRs in the past 18 years. We have successfully transitioned multiple disruptive technologies, including our distributed damage detection system, which was licensed to Raytheon Technologies in 2016, and a CNT-based electrothermal de-icing system licensed in 2018 to Goodrich. Since it is impossible to test new materials and structures under all possible configurations and load conditions, this leads to unreliable predictions for performance degradation and failure of a structure. This drives conservative inspection, maintenance, and retirement cycles, and also drives up systems weight and can moderate performance of an asset due to large margins of safety that are applied. Therefore, the Navy has a need for reliable systems for assessing the state of structural health of a structure in order to accurately diagnose precursors to visual damage and be able to provide structural prognostics for condition-based maintenance. Structural health monitoring, or SHM systems, detect and interpret adverse changes in a structure with the goals of reducing life cycle costs while improving reliability and asset availability. These systems can be implemented in several different ways, ranging from on-demand NDE, where essentially you can facilitate NDE at a push of a button, real-time assessment, where systems are constantly monitoring a structure in order to see if a certain damage event, such as bird strike or battle damage, would affect the ability of an asset to fulfill its mission. And finally, hotspot monitoring, where you are persistently and aggressively evaluating the health of a specific failure critical or known problem area. There are a couple problems with existing approaches. These traditional approaches, first of all, require high sensor densities. This is because most detection methods can only detect damage directly beneath the sensor location. So to cover damage over a very large area would require either many sensors or very large sensors, both of which can be very impractical. Second of all, most existing strategies are analog and do not scale practically. You essentially have a distribution of these many sensors, and you have individual wires running from each of those sensors to a central location, which adds a lot of mass and costs for installation. The MD7 digital SHM system seeks to resolve both of these issues. It uses a novel sensor and algorithm design to be able to cover a large area from a single sensing element, and it uses distributed intelligence on a digital sensor bus in order to reduce the total mass of the system. The first main element of the MD7 system is the structural sonar. This is the analog sensor that facilitates pitch catch and pulse echo ultrasonic guided wave testing. Essentially, it's equivalent to an active or passive sonar system that's scanning an area of roughly 1 to 2 meters in radius, depending on material, looking for changes in structural stiffness. The other two elements of the MD7 system are the acquisition and accumulation hardware nodes. The acquisition node is essentially the distributed data acquisition system that sits on top of each sensor element to facilitate both signal excitation and data digitization to send it along the digital bus. A single accumulation node sits on the bus in order to facilitate collection and storage of data and synchronize all of the data points. Multiple accumulation node buses can reside on the same asset and all connect over Ethernet to a Pulse tablet ground station. As previously mentioned, Raytheon Technologies holds an exclusive license to manufacture and sell the MD7 system. They also manufacture and sell the Pulse tablet and its custom software required for individual applications. At each node location, a phase-coherent, location-independent sonar scan is being performed using beamforming algorithms. As you can see in this figure, the color represents the number of standard deviations that the current structural stiffness data changes over damage-free data taken initially. All of this data is then sent to the pulse ground station to be able to be summed incoherently to form a composite image. Logic is then applied in order to compensate for view area obstacles such as holes and boundary conditions. This slide presents data from the Triton full-scale test article, where we had over 24 nodes installed on the Triton wing as it was displaced by more than 20 feet. Every 90 seconds, we collected data, which resulted in a sonar scan similar to the image in the middle. This again is comparing a baseline condition to the current condition and showing the number of standard deviations from that condition. At some point during testing, several delaminations formed between the Triton skin and the Triton ribs, which you can see illustrated on the image on the right-hand side. The red areas are areas that were indicating very high probability of damage, where the white ovals are representing actual NDI data of where they found damage. On the left, we show the resulting trends, which essentially are just integrating the energy from each of these scans. And you can see basically very little change until the point where there was damage, and then at that point, it did not restore back to the baseline condition. For comparison, our scans took 90 seconds compared to the 3 weeks that it took in order to perform manual inspection of these wings. We've been able to mature this technology to a TRL-7 for multiple applications. For ships, we've installed 14 of these sensors on the LCS-2 USS Independence back in 2012, where we collected data continuously at sea for over 4 years and correctly identified that no damage was present. Thereafter, it was expanded to a different section of the ship that had known damage, where we monitored from 2015 to 16, tracking that damage growth. For rotorcraft, we've participated in 4 major programs with Sikorsky under Army and Navy funding, which included over 250 tests on the Black Hawk and the CH-53K, both subcomponent and full-scale test articles. Currently, we're performing flight testing for both the S-92 and the CH-53K. For fixed-wing aircraft, we've conducted flight testing on the C-5, where we installed 26 sensors on the troop deck, and soon we'll be participating in full-scale testing on the Triton as well. Finally, 4 separate systems have been launched into space through AFRL, 3 of which onto ISS, and 1 on an Air Force satellite. As this is a relatively mature technology, we are currently seeking program office support for new Phase 3 applications. Please stop by my virtual booth in order to discuss new applications, or I can be reached anytime using the contact information you see on your screen right now. Thank you so much for listening to my presentation, and I hope to be able to talk to you soon.